Good night, everyone, and welcome back. Let's review an FENP sample question in a structural analysis. In this example, we have a cantilever beam of AB handling a triangular loading. Start at support A with the amount of W and reaches to 0. So if we have like a rectangular loading, the resultants applied at the center, and that's equal to load times the length, if assuming the length of the beam is L. And then for our case, the resultant is equal to the loading is half, so that's W, uh, half of WL, and the location of the resultant is 1/3 of L for a triangular loading. We want to calculate the maximum deflection which occurs at the free end B. So delta maximum at B is equal to what? So the easiest approach, or one of the easiest approach to get this answer is, like, first of all, getting the reaction at A. So there is only one reaction, we call it R sub A, and that's equal to resultant force, which is a half of WL. So the resultant force, which is a half of WL, should cancel out but by the only reaction, which is RA. And then MA is nothing but the moment is arm times force. That's our moment. So MA is WL squared over 6. That's how we get the moment at A and also the reaction at A. So as soon as we have that, our solution is based off moment area method. So we need to draw the shear and also moment. So by drawing the deflected beam, we can easily see this is delta B, and based off the second moment area theorem, delta at B is tangential deviation of B with a horizontal line which passes through the reaction at A. So, and that's exactly the amount of deflection at B, that's equal to delta B. By having, like, we do know this is the linear loading or first degree for our loading, so definitely our shear would be second degree. Mhm. So it just started, goes up with the amount of the reaction at AWL over 2 and eventually reaches to 0, which there is no shear at B. Mhm. So one may argue why this is not the path of our shear diagram. So again, this is the start of the top one, also start at WL over 2 and reaches to 0 at B. For understanding that, we have to look at the pattern of decreasing pattern of load. So it says the slope of shear should decrease. It decreases, decreases, decreases until it just goes to 0 slope at B. But the top one, there is a 0, but the slope is increasing, this which is not correct. That's why the top one is not acceptable, and this is the true form of drawing the shear diagram. So again, this is second degree, and as soon as we have shear diagram, we can jot down to jump to the moment diagram and draw the moment diagram. So if the shear is second degree, definitely the moment is a third degree. The amount of the moment at here is WL squared over 6. That's RMA. And it just uh, goes to 0. There is no moment at B. And again, one may argue why we cannot go this way. Again, it is 0 at B and WL over 6 at the support. But again, for understanding the correct moment diagram, you have to look at the shear diagram. If you look at the shear diagram, you can easily see the amount of shear is decreasing. It just says the slope of a moment should decrease and eventually shear is zero, so the slope of moment is zero. But if you go to the bottom diagram, it just says the slope of moment is increasing and it's not zero. It's a the vertical line. It's at B, and so that's not the correct form of moment. So the correct answer is this diagram. So if we divide it by E over EI, and easily you can easily see if this is third degree, we have a rule like if this is L, this is L over n plus 2. So the distance to the base of the centroid, that's L over 5. And if this is L over 5, the other part is 4 over 5 of L. So now let's jump to the calculation of mm, delta B, which is tangential deviation of B with respect to A, and that's based of second moment of area, that's M over EI, the area under moment diagram, times X bar, which considered from point B, because that's tangential deviation of B with respect to A. So the measurement is based off B, or first point. So M over EI times 4 over 5 times L. So this is the area. If this is the third degree, the area is L over n plus 1 BH. So that's 1/4 of WL squared over 6 EI, which is the amount of our base, times the total length, which is L. So this is the area times, this is our X bar, which is a 4 over 5 times L. And if you do the math, it just gives you the delta at B is equal to WL to the force over 30 EI. Thank you. We'll solve more problems in beam deflections.